Hello everyone, myself Soumya Vijay, Assistant Professor, Department of ECE SJBIT. Department of ECE SJBIT. Okay, in this session I will be discussing about the Module 3 topic of microwave and antennas. It is about strip lines and antenna basics. In this session I will be discussing about the topic microstrip lines. In the previous session we discussed about the construction for the strip lines and what is the characteristic impedance of the strip line. In this session we will be discussing about the next topics of strip lines. Let us discuss about the losses in the microstrip lines. For a non-magnetic dielectric substrate, there are two types of losses which occur in the dominant microstrip mode. One is the dielectric loss in the substrate, another is the ohmic skin loss in the strip conductor and the ground plane. We are considering a non-magnetic dielectric substrate, and for this we can tell that there are two types of losses which occur in the dominant microstrip mode. One is the dielectric loss which occurs in the substrate, and one more loss occurs in the strip conductor as well as on the ground plane, which is named as ohmic skin loss. And the sum of these two losses may be expressed as the losses per unit length in terms of attenuation factor A. These losses, that is dielectric loss and ohmic skin loss, they can be expressed as the summation, and they can be expressed as losses per unit length in terms of attenuation factor A. One more loss is present in the microstrip line which is named as radiation loss. Let us now discuss about the dielectric losses. In a lossy dielectric material, the conductivity cannot be neglected. So this results in electric and magnetic fields in the dielectric which are no longer in time phase. In a lossy dielectric material, the conductivity cannot be neglected. Hence, the resulting parameter will be electric and magnetic field in the dielectric, and they will be no longer in time phase. In that case, the dielectric attenuation constant can be expressed in equation form as alpha d is equal to rho by 2 square root of mu by epsilon Napiers per centimeter, where rho is the conductivity of the dielectric substrate board in mho per centimeter. The dielectric attenuation constant is expressed as alpha d is equal to rho by 2 square root of mu by epsilon Napiers per centimeter, where rho is the conductivity of the dielectric substrate board in mho per centimeter. Now, the dielectric constant can also be expressed in terms of dielectric loss tangent, which is given by tan theta is equal to rho divided by W epsilon. The dielectric constant can also be expressed in terms of dielectric loss tangent, which is given by tan theta is equal to rho divided by W epsilon. Substituting this into above equation, we get the dielectric attenuation constant as expressed by alpha d is equal to W by 2 square root of mu epsilon into tan theta Napiers per centimeter. Now, since the microstrip line is a non-magnetic mixed dielectric system, microstrip line is a non-magnetic mixed dielectric system. The upper dielectric above the microstrip ribbon is air. Above the microstrip ribbon, whatever upper dielectric is there, that is air. So, Welsh and Pratt, they derived an equation for the attenuation constant of a dielectric substrate. Accordingly, since microstrip line is a non-magnetic mixed dielectric system, the upper dielectric above the microstrip ribbon is air. So, Welsh and Pratt, they derive an expression for the attenuation constant of a dielectric substrate, and is given as alpha d is equal to 4.34 q rho divided by square root of epsilon r e into square root of mu naught by epsilon naught. This can also be written as 1.634 into 10 power of 3 q rho divided by square root of epsilon r e dB per centimeter. Welsh and Pratt, they derived an expression for the attenuation constant of a dielectric substrate, which is given as alpha d is equal to 4.34 q rho divided by square root of epsilon r e into square root of mu naught by epsilon naught. This can also be written as 1.634 into 10 power of 3 q rho divided by square root of epsilon r e dB per centimeter, where the Q, that is dielectric filling factor, is given as Q is equal to epsilon r e minus 1 divided by epsilon r minus 1, where Q, that is dielectric filling factor, is given as Q is equal to epsilon r e minus 1 by epsilon r minus 1. We usually express the attenuation constant per wavelength as alpha d is equal to 27.3 into q epsilon r divided by epsilon r e into tan theta divided by lambda g dB per lambda g. Usually we express the attenuation constant per wavelength as alpha d equal to 27.3 into q epsilon r divided by epsilon r e tan theta divided by lambda g. The unit is dB per lambda g because this is attenuation constant per wavelength. Here the lambda g is equal to lambda naught divided by square root of epsilon r e, and lambda naught here again is the wavelength in free space, or this can also be written as lambda g is equal to, since lambda naught is wavelength in free space, this can be written as c by f. So in the place of lambda naught, substitute c by f into square root of epsilon r e. Here c is the velocity of the light in vacuum. So the attenuation constant per wavelength is given by alpha d is equal to 27.3 into q epsilon r divided by epsilon r e into tan theta by lambda g. The unit is dB per lambda g, where lambda g is lambda naught divided by square root of epsilon r e. Lambda naught is the wavelength in free space, or lambda g can also be written as c by f into 1 by square root of epsilon r e, where c is the velocity of the light in vacuum. Now let us discuss about the second type of losses called ohmic losses, which occurs due to the conducting material. In a microstrip line over a low loss dielectric substrate, the predominant sources of losses at the microwave frequencies are the non-perfect conductors. The current density in the strip conductor and the ground conductor is not uniform in the transverse plane. In the transverse plane, whatever current density is there in the strip conductor and the ground conductor, both will not be uniform in the transverse plane. So the microstrip conductor, it will contribute for the major part of the ohmic loss. Now, the conducting attenuation constant due to these ohmic losses of the wide microstrip line can be expressed by the equation. The conducting attenuation constant due to ohmic losses of the wide microstrip line can be expressed by the equation as alpha c is almost equal to 8.686 Rs divided by Z naught into W dB per centimeter. This is for W by H greater than 1. Therefore, the conducting attenuation loss constant due to ohmic losses of a wide microstrip line, for a wide microstrip line, that is why W by H is greater than 1, is given by alpha c almost equal to 8.686 Rs divided by Z naught into W, where Rs is square root of pi f mu divided by rho is the surface skin resistance in ohm per square, where Rs equal to square root of pi f mu by rho is the surface skin resistance in ohms per square. Rs is equal to 1 by delta rho is ohms per square, and delta is equal to square root of 1 by pi f mu rho is the skin depth in centimeter. Now let us discuss about another type of losses called radiation losses. And what this radiation loss is dependent is, it is mainly dependent on substrate thickness and the dielectric constant as well as its geometry. The radiation loss is dependent on the substrate thickness, the dielectric constant as well as its geometry. According to the Levin's results, the ratio of radiated power to the total dissipated power for an open circuited microstrip line can be given by P rad divided by Pt is equal to 240 pi square into h by lambda naught the whole square into f of epsilon Re divided by z naught. The ratio of radiated power to the total dissipated power for an open circuited microstrip line according to Levin is given by P rad by Pt is equal to 240 pi square into h by lambda naught the whole square into f of epsilon Re divided by z naught, where f of epsilon Re is a radiation factor and it is given by f of epsilon Re is equal to epsilon Re plus 1 divided by epsilon Re minus epsilon Re minus 1 divided by 2 epsilon Re square root of epsilon Re ln of square root of epsilon Re plus 1 divided by square root of epsilon Re minus 1. The radiation factor, actually it decreases with increasing substrate dielectric constant. The radiation factor, it decreases with increasing substrate dielectric constant. So, the equation can be expressed as P rad divided by Pt is equal to Rr divided by Z naught, where Rr is the radiation resistance of a open circuited microstrip and Rr is given by 240 pi square into h by lambda naught the whole square into f of epsilon Re, where f is the radiation factor. Now, the ratio of the radiation resistance Rr to the real part of the characteristic impedance Z0, the ratio of Rr to Z0 of the microstrip line is equal to small fraction of power radiated from a single open circuit discontinuity. We can tell that the ratio of Rr radiation resistance to the characteristic impedance Z0 of the microstrip line is equal to the small fraction of the power radiated from the single open circuit discontinuity. And this radiation loss, it decreases when the characteristic impedance increases. As you can notice here, these two are inversely proportional. So, whenever the radiation loss decreases, it tells that the characteristic impedance increases. For lower dielectric constant substrates, the radiation is significant at higher impedance levels. Whenever we consider higher impedance levels, the radiation is very much significant, and this is for lower dielectric constant substrates. Now let us discuss about the parallel strip line. The parallel strip line consists of two perfectly parallel strips separated by a perfect dielectric slab of uniform thickness. Thickness is D. There are two perfectly parallel strips, that is nothing but conducting material, which are separated by a perfect dielectric slab having the mu d and epsilon d as the permittivity and permeability value. The plate width is W, the separation distance is d, and the relative dielectric constant of the slab is epsilon Rd. Relative dielectric constant of the slab is epsilon Rd. This is how the parallel strip line is constructed. It consists of two perfectly parallel strips which are separated by a perfect dielectric slab of uniform thickness. The plate width is W, the separation distance is d, and the relative dielectric constant of the slab is epsilon Rd. Let us discuss about the distributed parameters of this parallel strip line. In a microwave integrated circuit, a strip line can be easily fabricated on a dielectric substrate by using printed circuit techniques. A parallel strip line is similar to a two conductor transmission line. We can relate a parallel strip line to a two conductor transmission line because there are two strip lines which are placed parallelly. So, we can relate that to two conductor transmission line. So, we can tell that it supports a quasi TEM mode. It supports a quasi TEM mode. Now, consider a TEM mode wave propagating in the positive z direction in a lossless strip line. Lossless strip line in the sense R is equal to G is equal to 0 and there is a TEM mode which is propagating in the positive z direction. The electric field is in the y direction and the magnetic field is in the x direction. Sorry, here the electric field is in y direction, it is not mentioned. And if the width W is much larger than the separation distance, the fringing capacitance is negligible. Suppose if the width W is larger than the separation distance means the fringing capacitance can be negligible, as the equation for the inductance along the two conducting strips can be given by L is equal to mu c into D divided by W Henry per meter, where mu c is the permeability of the conductor. L, the inductance for the conducting strip, is given by mu c into D by W Henry per meter, because mu c is the permeability of the conductor. The capacitance between the two conducting strips can be expressed as C is equal to epsilon D W by D farad per meter, where epsilon R or D is the permittivity of the dielectric slab. Similarly, the series resistance for both the strips is given by R is equal to 2 Rs divided by W, that is equal to 2 by W square root of pi f mu c by rho c omega per ohms per meter. The shunt conductance of the strip line is given by G is equal to rho d W by D mho per meter. Now, the characteristic impedance for a lossless parallel strip line is Z0 is equal to square root of L by C. The characteristic impedance is given by square root of L by C, that is equal to D by W square root of mu D by epsilon D, that is equal to 377 divided by square root of epsilon R D into D by W, or W very much greater than D. Now, the phase velocity along a parallel strip line is Vp is equal to omega by beta. We have already learnt about this. We know the phase velocity for the transmission line, that is given by Vp, that is omega by beta. Same we are applying for parallel strip line EM, that is equal to 1 by root of Lc. After doing the substitution for L and C, we get the expression as C by square root of epsilon R D meter per second, where mu c is equal to mu naught. Now, let us write the characteristic impedance for a lossy parallel strip line. Lossy parallel strip line at microwave frequency, it means R is less than W omega L, G is less than WC, that is omega C. It can be approximated as Z0 is almost equal to square root of L by C, that is equal to 377 divided by square root of epsilon R D D by W, for W very much greater than D. Now, let us find out what is the attenuation loss. The propagation constant of a parallel strip line at microwave frequencies is given by the propagation constant gamma is equal to square root of R plus j omega L into G plus j omega C, for R very much less than omega L and G very much less than omega C, that is equal to, after the substitution of R, L, G and C, is almost equal to 1 by 2 into R into square root of C by L plus G into square root of L by C plus j omega rho square root of Lc, and those therefore, the attenuation and phase constant, that is alpha and beta, because gamma, the propagation constant, is a combination of alpha and beta, that is equal to alpha plus j beta, that is equal to what? Alpha plus j beta, that is the propagation constant. So, we can segregate the terms pertaining to attenuation and phase constant now. Accordingly, alpha is equal to 1 by 2 r into root of c by l plus g into root of l by c, that is the magnitude value. The unit is Napiers per meter, and similarly beta is nothing but the imaginary part. It is given by omega root of LC radians per meter. Now, substitution of the distributed parameters of a parallel strip line into equation, it yields the attenuation constants for the conductor and dielectric losses. Therefore, alpha c is equal to 1 by 2 r square root of c by l, that is equal to 1 by d square root of pi f epsilon d divided by rho c Napiers per meter. Similarly, alpha d can be written as 1 by 2 g square root of l by c, that is equal to 188 rho d divided by square root of epsilon d Napiers per meter. This is about the equations pertaining to the attenuation losses. Next we have coplanar strip lines. A coplanar strip line consisting of two conducting strips on one substrate surface with one strip grounded. It consists of again two conducting strips on one substrate surface with one strip grounded. The coplanar strip line has advantages over the conventional parallel strip line because its two strips are on the same substrate surface for convenient connections. Now, in microwave integrated circuits, the wire bonds have always presented reliability and reproducibility problems. So, the coplanar strip lines eliminate the difficulties involved in connecting the shunt elements between the odd and ground strips. As a result, the reliability is increasing, reproducibility is enhanced, as well as the production cost is decreased. Therefore, the characteristic impedance of a coplanar strip line is Z0 is equal to 2 P average divided by I naught square, where I naught is the total peak current in one strip and P average is the average power flowing in the positive Z direction. Average flowing power can be expressed as P average is equal to 1 by 2 real of surface integral E cross H conjugate into UZ dx dy, where Ex is electric field intensity in the positive x direction, Hy is the magnetic field intensity in the positive y direction. This is how the coplanar strip line looks like. There are two strips here, that is why we call it as coplanar. Let us now understand a problem related to the coplanar strip line. It carries a average power of 250 milliwatt, a peak current of 100 nanoamps. Determine the characteristic impedance of the coplanar strip line. The characteristic impedance of coplanar strip line is Z0 is equal to 2 into 2 times the average power, that is 250 into 10 power of minus 3 divided by I square, P, that is peak current square, that is 100 into, it is milliamps, sorry, this is R, this is not Rn, this is milli, this is milliamps. So, 100 into 10 power of minus 3 the whole square, that is resulting in the impedance value 50 ohms. Next we have shielded strip lines. A partially shielded strip line has its strip conductor embedded in a dielectric medium and its top and bottom ground planes have no connection. As you can see here the dielectric strip conductor is been embedded in this dielectric medium having the thickness d, and this strip conductor has got width t and this length is w, and this is present in the dielectric medium having the epsilon r value, and this is how the characteristic impedance of Z0 of a line with the t by d ratio as a parameter is been plotted. The characteristic impedance for this wide strip, that is w by d greater than 0.35 is given by Z0 is equal to 94.15 divided by square root of epsilon r into w by d k plus Cf divided by 8.854 epsilon r whole power of minus 1, where k is given by 1 by 1 minus t by d. T is the strip thickness, d is the distance between the two ground planes, and Cf is given by 8.854 epsilon r divided by pi into 2k ln of k plus 1 minus k minus 1 ln of k square minus 1, and is the fringe capacitance in picofarad per meter. This is about the discussion with respect to the losses of the microstrip line, as well as the discussion with respect to the parallel strip line, a coplanar strip line, and shielded strip lines. Thank you.